It's amazing to be here and with a beautiful venue and lovely weather and lovely people. And thanks for the very concise introduction. So I'm here today to, by the way, that glitch in the animation happens on the website. I don't know, not my fault. I'm here today to talk about a new project we took on, which is a C++ font subsetter. And before I get into it, I want to give a shout out to the Google Fonts engineer who actually implemented this, Rod and Garrett sitting there. If it wasn't for Rod's insistence and Garrett's coding, I wouldn't have anything to demo today. That said, it's a work in progress. It probably takes another year to be fully functional. It's already functional, but for a subset of things that we wanted to do. So maybe next year I can report on how things went. But most of this talk is going to be looking back on what we had and what the problem space was and how we addressed it before, what the limitations were, and why we had to take on this new project, and what are some of the design considerations. So what is font subsetting? To some of us, it's very familiar because we've been dealing with it all day, but font subsetting in short is producing a new font from an input font that behaves like the original, but with reduced functionality, for the purpose of mostly saving byte size or for compatibility reasons, and then based on a subsetting specification. Now, what I mean from an input font to an output font, we're really just working on binaries here. This has nothing to do with source formats like like UF or Glyphs or SFD. This is not about a font building pipeline, which is what we did before. And for the sake of the rest of this presentation, we leave out the web font delivery formats WAF and WAF2 and EUT because they are external post-processing or pre-processing that happen. We are just focusing on the subsetting operation. And when I say the output font behaves like the input, that's where many of the subsetters before failed. This involves full functionality of open type features, complex layout. Basically, the output font should work correctly and functionally equivalent. And the functionally equivalent, I mean, it might not be byte to byte or structure to structure compatible, but from a user's point of view, it makes no difference. Reducing font file size can happen by, or reducing functionality can happen by reducing glyph set. That's one thing that many designers do in their production, or for web font delivery, we do a lot. But it also involves reducing discretionary ligatures and other layout features, or reducing the variation space, since everyone's talking about variations recently, or dropping other features from a font to save byte size, like hinting, glyph names, bitmaps, legacy tables. Or for compatibility reasons, like, for example, generating a PDF or XPS file, a variable font will not work, so you may want to instantiate it, or for other reasons, or older software that does not understand certain things. Based on a specification, so for the purpose of the subsetting operation, we have an input file and a specification of what we want the output to support. That involves the character set, layout features, name table entries, and other options. So that's what subsetting is about. Now, why do we need subsetting? The main purpose, for at least the interest for my job, is web font delivery. When you have a Chinese page that wants to use a web file, you don't want to download the 16 megabyte Lotus and CJK. Same thing if you are printing to PDF. When I did the subsetter originally, that was the main motivation, but I found that many designers found it increasingly useful as part of their workflow, so they can always generate the full font, the pro font, and then just subset it to limited character set or limited features to sell it at a reduced price. It's also used for optimizing fonts for a specific system. For example, if you are shipping or delivering font over the web to Android device with a high resolution. We don't do hinting on the Android, so we can drop hinting, or you are shipping to Windows or Mac OS, same thing, or other kinds of tailoring to a specific system. Font streaming is interesting. Let me quickly define what I mean by that. I already mentioned the Chinese, Japanese, Korean problem. If you have a web page, you can't download the 16 megabyte Notus and CJK, but really there's not much else you can do because these languages don't have a small character set to cater to. So what many companies, Google, Monotype, Microsoft, and Adobe independently have developed is a solution based on JavaScript or other system to deliver only parts of the font, basically only the glyphs for characters that the page uses. And that's what we mean by font streaming. And at the last W3C Web Fonts Working Group meeting, there was this suggestion that the working group should take on the problem of font streaming to standardize it, because it's clearly a use case that everyone needs. And having a super fast subsetter can be part of such a solution. Printing also uses subsetting. Whenever you print a PDF or a printer, again, you don't want to ship the entire 16 megabyte font in the PDF, so you just subset it to the used glyphs. But printing subsetting is also more of a backward-looking problem. You typically have to support all kind of old legacy font formats like Type 1. And so it's not the primary goal of this work, but in the future, I can see Chrome and Firefox and LibreOffice switch to using this subsetter for printing as well. So that's why subsetting is needed. So now, what we have been using is what I call the font tool subset module, or also known as PIFT subset. That's a horrible name I chose. It started back in 2013, and there's a story I'm not sure I should share, but David Coutal, the head of the Google Fonts at the time, has been asking me for a subsetter, and back then they were using the subsetter written in Java called Fontly that was a very limited subsetter. It didn't understand, it didn't know how to subset OpenType layout features, so it was very limited to Latin and drop-in kerning and ligatures on the way. So there was a need for a more capable subsetter, and I had told him repeatedly that, yeah, I will do one in HarfBuzz, but that didn't happen. And the more I thought about it, the more work it was. And 5 years ago, me didn't know what I know now. However, there was a meeting where a big company, provider of fonts and font technology, came to David Coutal and said, yeah, we have developed a OpenType subsetter in Python, prototype, and then we just need to port it to C++. Do you want to license it? And then I messaged David immediately, and I said, the Python thing they say, I can do in a weekend. And then I did that. So I built it on top of FontTools. FontTools does already load the font and knows how to save the font. And I was super familiar with the GSUB and GPOS tables because that's what I've been doing for 20 years. So I said, okay, over the weekend I developed a subsetter for GSUB and GPOS tables, and I showed it to David next day. And he said, that's great, but why is the glyph table the same size? I said, well, yeah, I thought you already have a glyph subsetter, but okay, 5 more lines, glyph subsetter. And then it went on, and after 2 weeks, I had a full subsetter for CFF and glyphs and everything. And then a couple months later, Rod joined the Google Fonts team, and he just pushed it on into production, and it has been there since. And then Garrett pestered me with a lot of slow cases, so I had to optimize it. And then originally, we were running this over Jython, which is a Java runtime running Python code in production at Google, and that slows the whole thing down by a factor of 2. So recently, again, Garrett ported this to run on CPython. I had to implement major speedups to make it keep going for a few more years, mainly just lazy loading all the tables. So if you have a huge font but only want to subset a few glyphs to show an ad or a headline, you don't have to load the entire font. That got us going up until now. Then primarily, Google Fonts only serves TrueType currently, so there was a lot of TrueType specific hacks or optimizations that went into it. It works fine for small fonts, but still for huge fonts like Notice and CJK, it's slow, and we have hit the limits of what you can do in Python, and I'll get into that. So when I say 5-line subset in glyph table, I literally mean it. This is how you can subset the glyph table of a font tools loaded font. But then after, so let's try this. Yeah. Basically just the glyph, self.glyphs is a dictionary from glyph names to glyph whatever structure. You just filter out the ones you don't want. That's that with optimizations that went into it to not load the entire glyph or not decode the glyph, then it becomes more complicated. You have to remap components. So, but still, this is the entirety of subsetting the glyph table in the Python subsetter. Now, the whole thing is about 3,000 lines of code. The more complicated parts are GSub and GPOS because that's just a lot of tables, and then you have to remove unused lookups, remove unused features, remap their numbers, and it's a lot of bookkeeping going on. And then CFF also is very similar. It uses subroutines, so you have to remove the unused subroutines and renumber the subroutines. So those two chunks are more code, but simple tables like glyph really have like 5-10 lines of subsetting code. Now, performance-wise, let's take a look. What I have here, 4 runs of the font tool subsetter over Roboto regular. And the first line, I'm just, let's see. Yeah, I'm just subsetting the first glyph, 10 first glyphs, 100, and 1,000. And I'm performing this to show how the runtime grows based on the number of output glyphs. What we are seeing here, there's already a quarter of a second, like 240 milliseconds, just purely loading the font, and that's a lot of time. That's for an online web application, that's prohibitively long. But as we grow, like for 1,000 glyphs, the time doubles, so we have like 200 milliseconds for 1,000 glyphs. That's like 0.2 milliseconds per glyph. That's still a lot of time. Yep. If I move to a font like Iran Nastaliq that has a more complicated GSub and lots of glyphs, and when you have GSub and complex text, subsetting becomes interesting because when you specify which characters you want, the subsetter now has to go do what we call a glyph closure to discover all the glyphs that can be accessed using these characters through GSub rules, and do that closure over the glyph set and subset that increased glyph set. So here we see 1,000 glyphs takes 1.5 seconds. And if you thought that's bad, Noto Nastaliq Urdu, which is also a Nastaliq style font, takes 4 seconds to subset 1,000 glyphs. That's just painful. Now, Noto Nastaliq Urdu is notorious for being complicated. When we first released it, it broke every piece of software. Chrome, Firefox, Cortex. Well, to their credit, it didn't break Internet Explorer. OpenType or CFF flavored fonts are slower. Here I have, well, I added a 10,000 glyphs at the end because Noto Sans CJK has that many glyphs. So here we see 700 millisecond loading time. That's just not acceptable in an online workflow. And for 10,000 glyphs, we are seeing like 10 seconds, 11 seconds. That's still 1 millisecond per glyph, too long. The reason the CFF is longer than TrueType, as I said, I optimized the TrueType. Also, Well, the major optimization for the true type part was to not decode the glyph coordinates and just ship the bytes out. Whereas for CFF, we have to decode the byte code, the char string, because we need to reference the used subroutines and renumber them. So CFF, there might be room to speed it up, but as I show, we are hitting the limits of what's possible in Python. Same font converted to true type is 5 times faster. So that just shows the true type optimizations compared to CFF. Now, let's get to how Python performs, because this informs us what's possible in Python to begin with. What I have here is just timing creation of an empty object. And you see it takes 84 nanoseconds. And the object class is not that interesting because it's slotted and doesn't do anything. If I import the simple namespace, which is just a subclass of object with no specifics, that takes twice the time. So that's 116 nanoseconds per loop. Let me translate what this means. 1 million of these operations takes 160 milliseconds. That's non-starter. 100,000 of them takes 16 milliseconds. Let's say that's acceptable. 100,000 object creation. When you have a font with 64,000 glyphs, that's less than 2 object creations per glyph. It just doesn't allow you to unpack the glyphs. So we are like orders of magnitude away from what Python can deliver. Here, just loading the CMAP table of Noto Sans CJK regular takes 113 milliseconds. And all the other tables in the font we have made lazy. The CMAP you still have to load. It's just, it's like changing that is such a drastic change to what Font Tools does. The first thing Font Tools does is to load the glyph order, the glyph names. And this just shows that as long as you load the glyph order and glyph names, you can't do any better. So hopefully I convinced you that we can optimize this any further in Python. So we have this beautiful subsetter, but it's just too slow. Now, in the redesigned subsetter, we want it to be fast, flexible, and secure. So what's the plan? Rewrite it in C++ and ship it. That's as simple as that. And it's a painful realization that when you're going from Python to C++, you don't need to think about it. It will be fast. But I wanted to have a more informed idea of what we are doing. The performance characterization of the redesigned subsetter will be guaranteed. The initialization of the font will be constant time, except if you want to keep the post table glyph names. That will, decoding that table takes the order of the number of glyphs in the original font. But that's the only place in the font format that there's no random access. If you don't want the glyph names in the true type font, the font loading is constant time, no matter how huge the font is. And then the subsetting time, so small n here is the number of chosen glyphs, output glyphs. The capital N is the number of the input glyphs. The C is the complexity of the font factor, depends on GSUB. And the B, small b, is the number of bytes the output font is. So I can guarantee this is the runtime of the subsetter. So there have been alternatives we could have considered, and I'll quickly walk you over why I didn't choose to use them. Sfontly is the original subsetter that the Google Fonts team was using. It was originally written in Java, but ported to C++ by the Chrome team to use for printing. It didn't have the GSUB or GPUs implemented or CFF, so it was basically a true type subsetter. I decided not to use it because What I have instead, what I'm going to use instead has better, it's a better platform to build on and provides me with safety and conveniences that I will talk about. OTS is the Open Type Sanitizer. It's, again, another project the Chrome team did. The goal was a security measure to protect browsers from malicious fonts that can trick the operating system. So if the Windows implementation of OpenType has a bug, Chrome wants to avoid hitting that bug by sanitizing the font file. It has grown to do other things like become like a lint for fonts. It sometimes likes to reject fonts because they don't fully adhere to the specification. But at any rate, it's kind of similar to a subsetter in that it reads the font and writes the font, but it doesn't provide any subsetting, so it doesn't get us any further. And OTFCC is another font compiler by the amazing Bell Invis, for those of you who know him. However, it's a font loading and saving framework with no subsetting. And as I will discuss later, I want no font loading, and I don't want font saving, and I want subsetting. So it's exactly the complement of what I want. So for the design of this new subset, we're going to use Pift subsets for inspiration on the user-facing interface, and we are going to use HarfBuzz code base for implementation. And HarfBuzz, for those of you not familiar with it, is a text shaper. That's the piece of code that takes care of complex scripts, ligatures, Arabic joining, index reordering, those things. The reason it's a very convenient place to design the subset on top is it knows very well how GSUB and GPOs work, and GSUB and GPOs are one of the more complicated parts of subsetting. It's also that it's a C++ library that I designed for specific design goals of security, robustness, speed, cross-platform, other design criteria that also can benefit a good subsetter. One of those criteria is the zero-cost loading. In HarfBuzz, we don't load the font file into any kind of internal representation or objects. What we do is just we map the font file into memory and access the bytes as needed, as if they were just regular integers and pointers. And a lot of that is well hidden by using a small subset of carefully chosen features of C++, namely operator overloading to do byte NDNS conversion, and use of small templates and types to hide a lot of the complexity of the table, and in particular to avoid loading anything. Memory safety is also guaranteed by the way we use C++ features, and we sanitize the tables before using them. And the strong type system, again, lets itself to very good and secure code that you can't accidentally use data the way it was not intended to be used. So I'm going to show a few pieces of code from other frameworks that deal with fonts. And this is a piece of code from FreeType, loading instant variation named instances from a font. And I had the pleasure of debugging this code because it was not performing well. And please spot the bug. A hint, if the font had an AVAR table, this code was not working correctly. And yes, I don't expect you to. The problem is, when there are these macros, FD get U short, or this frame enter, these things, they are C macros, they use this hidden stream parameter that keeps a pointer into the font file of where the font head is currently for loading. And if you hit this function, it loads the AVAR table and leaves the head of the font at some other place. So fixing this involved saving the file position and then seeking it back. So that was a not so much fun debugging experience. This is another piece of code. This one is from the font tool CFF module of an encoding converter. The converter basically just means reader. So it reads, the encoding type is passed in, it seeks to the correct position, and then reads the format. Depending on the format, it parses encoding formats 0 or 1. Again, there's a bug in this code. Can you spot it? Obviously not. This one is even more hideous. This parent.char set, when you access it, it calls the Python get@. If the char set is not loaded, it's loaded on demand, again moving the file position without restoring it. So your parse encoding completely parses the wrong data. So those are some of the kind of bugs that you can avoid by not having a file pointer to begin with and using immutable data structures and explicit references to locations. A friend of mine, Ibrahim, a contributor to HarfBuzz, recently contributed an implementation of the Apple track table. And while reviewing his work, the Apple specification leaves a lot to be desired, surprise. And I thought, well, Font Tools implements this table, so I can look at Font Tools to see the exact layout of the table and review the HarfBuzz code. I looked at it and I wanted to cry. Again, this code was correct, but not anymore. I introduced 3 bugs in it. Can you spot it? Impossible, right? Well, all the offsets were wrong. So it was reading, back. It's just impossible to understand what this is doing, let alone debugging it and spotting a bug. Same data structure in HarfBuzz. The full code for accessing and using it looks like this. This is essentially copy-pasted from the spec, just translated into our structures. This just says an unsigned integer, 2 byte, number of tracks, another one, number of sizes, and this is where we use the templates of carefully chosen templates. Says we have an L offset. L offset means long offset, meaning that the offset field is 32 bits instead of 16 bits. So a 32-bit offset to data of type unsized array of fixed numbers. Fixed is also defined as a specific number type in OpenType. And then this field, this offset, is followed by an unsized array of the track table entry. Track table entry is another data structure like this one. An unsized array of means that the length of the array is not stored with it, obviously because it's for this one it's stored here, and for the size table it's stored here. This up here is sanitize is the method we call to verify that font data is correct, and basically says, well, first make sure we can access all of these members, i.e. the table size is not too short for all these. Then we want to sanitize the size table. So we just sanitize it, and we have to give it the base. The base is where the offset is relative from. We also give it the number of sizes, because that's the size of the array, and to make sure the array doesn't go outside of the table, we need to have the size, and then we do the same thing for track table. After this function is called, we are certain that we can access this table without any memory problem or security problems. And the code using it can just access them as simple arrays. So this is for this kind of conciseness and structure that I wanted to do this in HarfBuzz, because all the other C++ solutions are a lot of read 2 bytes, write 2 bytes, and I didn't want that. So this is the structure of the Python subsetter. You load the font. For every table in the font, you prune it pre-subset, and the pruning is not the glyph subsetting operation, it's more of the other options. For example, if we don't want the legacy CMAP tables, this is where we drop them. We drop them early so we don't do extra work. Then we subset all the tables. This is only the glyph subsetting we are talking about here. And then after that, we do another round of pruning, post-subset. Some of the pruning options have a per glyph cost, so in that case, you want to do it after subsetting when you have fewer glyphs. So this is the general structure of the Python subsetter, and then you save the file. In the C++ one, I don't have loading. I have saving after the bytes are generated, but I wanted all these three combined into one path. Basically, you have the font mapped into memory. You get your specification, do whatever preparation you need. In one call, generate the output bytes, write it out. So 0 copy. You are not doing a single operation more than you have to do. So Garrett and Rod have implemented the true type, simple true type for this. G sub G plus GDEF is waiting on me to get started. CFF, CFF2 we do later this year, I assume. And then variable fonts instantiation and subsetting is part of the scope, but will not happen until next year, I would guess. Now, how does this perform? Subsetting Roboto for one character takes 0 milliseconds according to this timer. Subsetting for 64 characters, or is that 62, whatever, also 0. It's just you cannot measure the performance of this using this counter. It's 1,000 times faster than the Python one according to Garrett's measurements. It's also flexible because it's built on top of this modern healthy code base that is changing routinely and maintained and improved. And it's secure by design, but also thanks to this project, also by Google, called OSS Fuzz. It's a systematic fuzzing engine using the Google power for open source software. Fuzzing, for those of you not familiar, is this process of feeding carefully chosen random data into a process and trying to break it. And when you break it, you report it to the developers to fix it. And from the beginning, the subsetter is hooked up to OSS Fuzz, thanks to Garrett again. So the way this works, you write your code, you can be careless about it, doesn't matter. The next day, you get bug reports if you messed up sometime. And that gives us a lot of confidence in what we can do with this. HarfBuzz shaping is hooked up to OSS Fuzz. HarfBuzz subsetter is free type, OTS. All these font projects are now being fuzzed by OSS Fuzz. And when I say feeding random data into the process, I mean thousands times a second, ongoing for days, forever. So it's a lot of monkeys can write Shakespeare kind of thing. And foxes are from the Hourly Fox Twitter account. And with that, we get to questions or discussion, or tell me where you want this to go, what you want from the subsetter, what can you do with it. Thanks. Thank you.